Okay, so this is a continuation of the loop-the-loop problem. And the loop-the-loop problem starts as a force problem because it's all about the centripetal acceleration. But pretty much if you ask any other questions about this, like how fast are you going at the bottom of the loop, or how fast would you have to be going, say, at some place on a ramp, or even how high on a ramp would you start to make it around the loop if you started from rest, all of these questions are then energy questions. And so when you're doing energy problems, the basic idea is this, that if you have no work that's done on a system that's external to the system and done by some non-conservative force, then you can say that the work, the external work, or the non-conservative work, is equal to zero, which means that the change in the potential plus the kinetic plus potential, is equal to zero. The other way that you can say this is that the work done by gravity is equal to the change in the kinetic energy. These two statements are actually completely equivalent. So we're going to go ahead and do the second case here just to illustrate our point. See other problems in this set for examples of using potential energy. Okay, so the idea is, for example, if we have the loop-the-loop, so here's the loop-the-loop again, and we know that the speed at the top, is square root of gr, we can ask ourselves, what does the speed at the bottom have to be? And the speed at the bottom, well, let's see, if it's some radius of the loop is r, then that means that you are 2r below where you were at the top of the loop when you're at the bottom. So we can say that the work that's done by gravity to get you to the bottom is equal to the change in the kinetic energy from top to bottom. So the work that's done by gravity is just the force, mg, times the component of your path that's in the vertical direction, which is just 2r. Now I want to point something out. If you have a curvy path or some freaky path or whatever, or maybe you just have a straight path, it actually doesn't matter. You only need the component that's in the direction along the force. You only need this height h. So that it's a curved path, well, makes it a lot harder to solve with forces because now the force is not constant. You can't just use kinematics. Okay, so the work that's done by gravity is mg times that vertical distance. Why? Because gravity is a vertical force, and that's going to be the change in kinetic energy. So you get 1/2 mv squared final at the bottom minus 1/2 mv squared initial at the top. So we have 1/2 mv at the bottom squared minus 1/2 m, and now v squared at the top goes down here, so we get g times r. That's pretty much it. So all you have to do then is solve. So we'll divide each side by the mass, and then we get 2gr on one side, and we'll bring like terms together. So this is plus 1/2 gr, and I'm left with 1/2 v bottom squared, and if I multiply through by 2, I get 4gr plus gr is v bottom squared, which is 5gr. So the velocity at the bottom is the square root of 5gr, which is of course faster than gr, as you would expect. The other thing you can ask here is you can ask how high on an incline, on a ramp that leads into this. How high to start? Again, you can do this same problem, only now the work that's done by gravity is equal to the change in the kinetic energy. And now, right, at this point, you're going to start with no kinetic energy. So you're just going to have, say, the 1/2 mv bottom at the bottom minus 0 at the top. You're going to be released from rest. Okay, and so this is mg times the height of some ramp. So we have some ramp leading into the loop-de-loop. It has some height, h. And let's see, what was the question? Oh yeah, h. So we get that we divide by m, and we get that h is v squared at the bottom all over 2g, and v squared at the bottom was 5gr all over 2g. The g's cancel, and you get a really surprising result. 5/2 times r. That's how high you have to be. So remember, the height of the whole thing is 2r, and so you have to be one more half an r high to start and make it safely around the loop. That's if there's no friction, of course. But that's a story for another problem. Okay.